Hola chicos. Yo tengo un libro en español. Se llama Pobre Ana. Y mi maestra encontré el libro para mí. Y yo voy a leer el libro. Pero no comprendo todas cosas. Por ejemplo, ¿qué quiere decir pelo largo? Pelo largo. ¿Qué quiere decir? Y castaño. ¿Qué quiere decir castaño? Y yeah. No one's gonna help me out. No hay estudiante puede ayudarme. ¿Qué quiere decir pelo largo y castaño? No comprendo. Okay. Fine. I'm gonna start. All right. So today we are going to talk about gravity. You might have noticed that the quizzes are called circular motion and gravitation quizzes. So why? Oh, thank you. Gracias. I guess that it meant long hair, but I thought it meant maybe big hair. Like, I don't know. Okay, so castaño is brown. Okay, gracias. So, we're talking about gravity today. The reason we're talking about gravity with circular motion is because in the next lesson, we're going to talk about circular orbits of planets. And gravity is the centripetal force in that case, okay? So, Let's talk a little bit about the weight force. The weight force is, of course, we already learned about it. It's the force due to gravity. And the formula for the weight force is m times g, where g is the acceleration I'm not sure if I'm still streaming. I'm going to keep going. G is the acceleration due to gravity. And then m is the mass of the thing. Okay? Today, we are going to talk about what is called the gravitational field. Which is denoted by little g. And basically, the gravitational field is another word for acceleration due to gravity. So it's just a synonym for it. So you might see on the AP Physics 1 exam, you might see acceleration due to gravity, you might see gravitational field. Okay? So it's a synonym for the acceleration due to gravity. And so we could also write the gravitational force as m times g, where g is the gravitational field, okay, and m is the mass of the thing experiencing the field. Okay? So the units of acceleration due to gravity are meters per second squared. However, when we're talking about gravitational fields, another unit is preferred. Okay? So we take both sides of this equation, we divide by m, so we get little g equals F over m. And we can see that gravitational field is a force per mass. So we could also use the units newtons per kilogram. Okay, so this is the preferred unit when we're using the lingo of gravitational field. Okay, if we were talking about acceleration due to gravity, we could say meters per second squared. But important point is they're the same unit. So we could say the acceleration due to gravity at the surface of the Earth is 9.8 meters per second squared. Or alternatively, we could say the gravitational field at the surface of the Earth is 9.8 newtons per kilogram. We could say the gravitational field at the surface of the Moon is 1.6 newtons per kilogram. Or we could say the acceleration due to gravity at the surface of the Moon is 1.6 meters per second squared. So it's just different ways of saying the same thing. All right? So you need to know this vocabulary term, gravitational field. So the main question for today is, how can you calculate the gravitational field? Okay, this is our main question for today. And so, for example, we have measured that the gravitational field at the surface of the Earth is 9.8 newtons per kilogram. But is there a way that we could have predicted that in the first place? And the answer is yes, we can. Okay. So a couple things about the gravitational field. The gravitational field depends on how far away you are. If you move further and further away from a thing, the gravitational field due to that thing gets weaker and weaker and weaker and weaker. Okay? So if you're, at the surface of the Earth, the gravitational field due to the Earth is strong. Excuse me, it's strong. But if you move 10 light years away from the Earth, the gravitational field due to the Earth at that location is very, very weak. So it depends on how far you are away. All right? If you're in orbit around the Earth, there's a gravitational field. Okay? But it's weaker than what the gravitational field is at the surface. The other thing it depends on is the mass of the thing creating the field. Okay? So the more massive the thing is, the stronger the gravitational field that thing creates. So, for example, things like planets create large gravitational fields. Hang on one second. I'm gonna, because my computer is going like incredibly slow right now. So I'm gonna maybe close some windows. See if I can't free up some RAM. Maybe that worked. The computer's just going really slow right now. I probably just need to restart it. Okay, so the more massive the thing is, the greater the gravitational field it creates, regardless of the distance. Okay, so the person who figured it all out, who actually, wrote down the equation for the gravitational field was Isaac Newton, the same Isaac Newton who came up with the laws of motion. And so the law that he wrote down is called Newton's law of universal gravitation. Okay? And so here's the picture that we want to have in our heads when we're thinking about Newton's law of universal gravitation. Okay? You've got maybe a planet that is right here. The planet has a mass big M. So I use the Majin M from Dragon Ball to represent big M. Okay? So big M is the mass of the thing creating the gravitational field. And that, of course, depends on perspective. Okay, so if we're talking about us experiencing the gravitational field of the Earth, then m would represent the mass of the Earth. If we're talking about the Earth experiencing the gravitational field of the Sun, then big M would be the mass of the Sun. If we were talking about the Sun experiencing the gravitational field of the galaxy, then big M would be the mass of the galaxy. Okay? So it depends on your perspective. If we're talking about us experiencing the gravitational field of the Moon, this would be the mass of the Moon. Now, suppose we have like an astronaut who's over here. Okay? We are going to let R, big R, represent the distance between the centers. Centers of the objects. Okay? So not the distance to the surface, but the distance all the way to the center of the Earth. Okay? So right now we're on the surface of the Earth, so our R value would be equal to the radius of the Earth, because that's the distance from the surface to the center. Okay? All right. And so Newton wrote down an equation for the gravitational field, and it was little g equals big G times big M over R squared. Okay? And so this is our main equation for today. And it actually has all the information that I mentioned here. Okay? So in particular, we can see that R is on the denominator. So if you get further away from a planet, for example, the R value increases, which means the denominator increases, which means the gravitational field gets smaller. So the further you are away from something, the smaller the gravitational field you experience. And we can see that big M is in the numerator. So the more massive the thing is, the greater the gravitational field. Okay? Now, gravitational field is, of course, an acceleration. And accelerations have directions. So what is the direction of the gravitational field? Well, the direction, so in other words, which direction does gravity accelerate you in? Gravity accelerates you towards the center. Okay, so the acceleration due to gravity wants to accelerate us towards the center of the Earth. The reason that we don't accelerate towards the center of the Earth is because we also have a normal force which counteracts that gravitational force. So if you were right here, the gravitational field points towards the center. If you were right here, for example, the gravitational field points towards the center. All right? If you were right here, the gravitational field points towards the center. Now, I drew these arrows as different sizes because this astronaut is the farthest away from the center of the planet, so it has the smallest gravitational field arrow. This one is the second closest, so it has a medium length gravitational field, and this one is the closest, so it has the longest arrow representing the strongest gravitational field. Okay? So, this equation explains why black holes have some of the largest gravitational fields. It's because black holes are incredibly massive, so their M value is extremely large. And furthermore, black holes are actually quite small. Okay? At least the majority of there are supermassive black holes at the center of galaxies that are huge, but if we were to compress the Earth into a black hole, the size of that black hole would be about this big. For real, this is the literal size of the Earth as a black hole. It would be roughly the size of a marble. Okay, And so because it is so small, you can get really, really, really close to it and experience strong gravitational fields. Okay. Now this constant, big G, is not the same thing as little g. This is a constant of nature, big G, and it's called the universal gravitation constant. And I guess this is sort of our first example of a constant of nature. So constant of nature means that it's just a property of the universe, if you will. So this big G is the same number no matter what calculation you're doing. It's a constant of the universe, okay? So that's why it's called the universal gravitation constant. And its value is 6.7 times 10 to the negative 11. It has weird units, Newton meters squared per kilogram squared. Okay? So these are the important equations for important stuff for today. So why is it called the law of universal gravitation? Okay? The reason is, so there's a story, and I don't think it's a true story, but it's a story that people tell about Newton, is that Newton was sitting under an apple tree and an apple fell down and hit him on the head. Okay, so Newton has this apple hit him in the head, and he looks up, and it's one of those days where you can see the moon in the sky. Okay, so Newton makes the generalization that the same gravity that is pulling the apple towards the Earth is also the gravity that is making the moon orbit. Okay, and is the same gravity that is making the planets orbit, and it is the same gravity that is making the everything that's orbiting is orbiting due to the same law. There's a universal law describing gravity. Okay, so that was sort of the epiphany that Newton had. Okay, that you can generalize this law of attraction to any two objects. Okay, and really what big M is depends on your perspective. Okay, if we want to calculate what is the gravitational force on a person due to a planet, then big M is the mass of the planet, and little m in this equation right here is the mass of the person. Okay? But what if we wanted to calculate the gravitational force that the planet experiences due to the person? Then we have a role reversal. The thing creating the gravitational field would be the person, so big M would be the person, and little m would be the mass of the planet. So it's universal, okay? Everything that has mass creates a gravitational field. Everything that has mass creates a gravitational field. So we could calculate the gravitational field that you create by making you big M, okay? So you do create a gravitational field. But here's the thing. The gravitational field you create is really, really small. Why is that? It's because we take big M and we multiply it by big G, and big G is 6.7 times 10 to the negative 11. So that means if we wanted to write this not in scientific notation, we would have to move the decimal point 11 places to the left. So big G, ironically, big G is a really small number. So when we multiply your mass by big G, we get a really small gravitational field. Okay? But it does exist. Okay? Similarly, if you have, for example, an asteroid has a really large mass, but it's still not large enough to make a significant gravitational field. So there was actually a space mission where we landed on an asteroid, and the probe messed up on the landing. And instead of landing softly, it sort of bounced off the surface of the asteroid. And because the gravitational field that the asteroid created was so weak, the bounce took several days. So it hit the ground, it bounced, or it hit the surface of the asteroid, it bounced, and that bounce to come back took several days. So can you imagine being on the surface of an asteroid and jumping, and your jump would last a couple days? You might starve during the course of your jump. So I'll tell you a joke that I tell all my classes because I like it so much. Let's say you're on a date with someone. You're on a date. You got a hot date. You're sitting across the table from someone, okay? And you can say to them, "Can you feel the force of attraction between us?" And you would be correct in stating that, okay? You have mass, so you are creating a gravitational field that is causing the other person to be attracted to you by a very small gravitational force. So you can say that to them. You can say, "Do you feel the force of attraction between us?" And you're not wrong. There is a force of attraction, okay? So then maybe your date says, "No, I don't feel the force of attraction." So then what you do is you move closer to them. And when you move closer, that reduces the R value, which makes the gravitational field bigger, which increases the force of attraction. So they say they're not attracted to you. You move closer to them and you say, "How about now?" All right? Science. This is, of course, a joke. If someone says they're not attracted to you, you should not move closer to them. Okay? I feel that I need to say that. All right. So, there's another. We're going to do an example in just a second. In that example, but before I do the example, I want to just talk really briefly about density, which is something you probably learned about a long time ago, but I just want to review it because it's in today's quiz. Density in physics is typically denoted by the Greek letter rho. Okay, and rho is defined as mass per volume. Okay, so the units of density that are preferred in physics are kilograms per cubic meter, mass per volume. Okay, and so it's different from, chemistry where you might use grams per milliliter, grams per cc, or something like that. If we take both sides and we multiply by volume, we can solve for the mass. So this is one of the ways you could find the mass of a planet. You say, okay, the planet is made out of rock. Rock has a density of blah, blah, blah. So we can take the density of rock and multiply it by the volume of the planet to get the planet's mass. Okay. Planets are spheres, so the volume is the volume of a sphere, which is 4/3 pi r cubed. Okay. So you can use this equation to get the mass of the planet. There is a slight issue with this equation, which is this equation assumes a constant density, but the Earth does not have a constant density. It's actually, as you go further and further into the interior of the Earth, because of the increasing pressure, the density goes up. But we're not going to worry about that complicated situation. Okay, so let's do an example. Consider a planet made of rock of density 6,000 kilograms per cubic meter and radius 4.4 times 10 to the 6th meters. Calculate the gravitational force on a 90 kilogram satellite that is 2 times 10 to the 6th meters above the surface. Okay. So we're just going to do one example today because this has like all the stuff that we're going to need for the homework. So the first step here is we're going to be calculating the gravitational field, so we need big M. All right. So the first thing is we need to get the mass of the planet, and the planet is spherical. So we're going to use the equation mass of the planet is density times 4/3 pi r cubed. So the density is 6,000, and then we have 4/3 pi times the radius of the planet, which is 4.4 times 10 to the 6th cubed. Okay, so I type that into my calculator and I get, I did the same example last period, so I already know what the answer is. 2.1 times 10 to the 24th kilograms is the mass of the planet. Okay. Now I want to teach you how to use your calculator because scientific notation numbers on your calculator can be tricky. All right. So in particular, what if you wanted to cube 4.4 times 10 to the 6th? Okay. Some of you might be tempted to type this into the calculator. You would say, okay, 4.4 times 10 caret 6. That's a number you say, okay, cube it. This is wrong. This will get you the wrong answer. Okay? Whenever you're using scientific notation on a calculator, use an abundance of parentheses, okay? What we want to do, the correct thing to type in, is you put the entire scientific notation number in parentheses and you cube that. So this is the correct way. All right? Oops, to the third. That should be to the third. So just keep that in mind, all right? I'm trying to save you time on the homework, okay? Because the questions are really simple. The hard part is actually getting your calculator to do the thing that you want it to do, okay? All right, so now what we're going to do is we are going to calculate the gravitational field due to the planet at the location of the satellite. Okay? So we're going to use the equation little g equals big G times big M over r squared. Okay? So big G is going to be the same for every single gravitation problem. 6.7 times 10 to the negative 11. I can't remember if I said it already or not, but big G is different from little g, okay? You can't cancel out the g's on either side. So this is an example where it's case sensitive, okay? Big G is not the same as little g. Big G is a constant of the universe. M, I just calculated, is 2.1 times 10 to the 24th kilograms. And then we have to divide by the radius squared. Now, I'm going to pause for a second. We have to be really careful when we talk about big R, because what does big R represent? It represents the distance between the centers of the objects. Okay, so if this is the planet, all right, and the radius of the planet is R1, all right. Okay, the satellite has a certain altitude. It's a certain distance above the surface. R2, for example. Okay, so big R is the distance from the center of the planet to the center of the satellite. So we have to take into account both the radius of the planet and the altitude of the satellite. Okay, so big R is going to equal R1 plus R2, which in the case of our problem, the radius of the planet is 4.4 times 10 to the 6th, and the altitude of the satellite is 2 times 10 to the 6th. Which is 6.4 times 10 to the 6th meters. So, so this is 6.4 times 10 to the 6th. Now, we can see that we're going to have to divide scientific notation numbers. So here's what I want you to do. And I'm telling you to do the problem this way because it's going to save you time in the long run. Okay? I'm going to calculate the numerator and the denominator separately. Okay? So the numerator is 6.7 times 10 to the minus 11 times 2.1 times 10 to the 24th, which is 1.4 times 10 to the 14th. The denominator is 6.4 times 10 to the 6th squared, which is 4.1 times 10 to the 13th. Okay? Now, let me show you how some of you will be tempted, and probably some of you will still type it into the calculator this way despite my warnings. But some of you might type something like this into your calculator. You'll say, okay, 1.4 times 10 to the 14th, or sorry, I should say caret 14, divided by 4.1 times 10 caret 13. Seems like it should be right, but it's not. No, do not do that. You need to use an abundance of parentheses. So what you want to do is you want to put the entire numerator in parentheses. So 1.4 times 10 caret 14. And also put the entire denominator in parentheses. 4.1 times 10 caret 13. And divide those in parentheses. This is the correct way to do that. Okay? If you don't put the parentheses, because of the order of operations within the calculator, you will get the wrong answer. Okay? So this gives 3.4 newtons per kilogram as the gravitational field that the satellite experiences. Okay? So then our last step is to calculate the gravitational force. So gravitational force and gravitational field are two different things. Calculate the gravitational force the satellite experiences. So the formula for gravitational force is mass of the thing times gravitational field the thing experiences. Okay? So I have gravitational force equals mass times gravitational field. The thing experiencing the gravitational field is the 90 kilogram satellite. And the size of the gravitational field is 3.4 newtons per kilogram. So we get 307 newtons is the force that it experiences. Okay? So that is my lesson for today, and I will see you in the Zoom room. Bye for now.